Hi, this is Kylie, and this is my friend Stephanie, and today we're going to be talking about how black holes die. Okay, what do you know about black holes, Stephanie?
They suck in a lot of things.
That's true. You don't want to be near black holes. And black holes are actually these objects in space that have gravity that's so strong that not even light can escape. It's like wild. It's very wild. Basically, they have so much gravity because black holes are these points in space that are basically, they have infinite density. So they have some mass and it's shrunk into a point with basically zero volume.
How?
So density is mass over volume. And so if the volume is very, very small, it can get to very, very high density. So that's what they are. So how might you think that a black hole would die?
Maybe it like explodes.
It explodes?
Like you know the volume, you know how the volume is supposed to be really small, it gets big and then it's not a black hole anymore.
Wow, that's a wild idea. That's crazy. And you're right to think that it's probably not a normal process because black holes basically eat everything. We can't just, send in a bomb and blow it up to kill it.
Yeah.
Okay, it's just going to eat it and then it won't do anything. Mm-hmm. And so, in order to learn about how black holes die, there are two things we need to think about. So the first is that for every particle in the universe, there's an antiparticle. Mm-hmm. So for example, for electrons, there's what we call a positron. And so
that's different from a proton?
Yes, it's different. And so
Bro.
Yeah, there are lots of particles in the universe. So if you put a particle with its antiparticle together, they basically destroy each other and they annihilate and there's nothing left. Mm-hmm. And so that's the first concept we need to think about. Every particle has its antiparticle. And basically, we also need to think about this concept called vacuum energy. And in order to learn about vacuum energy, we need to understand something from this subfield of physics called quantum mechanics. So quantum mechanics tells us that we can't know the exact location of particles in the universe. There's just some probability of where it might be. And so because there's a probability of where it might be, we can kind of extend that to the vacuum of space and say, we think the vacuum of space is empty, but is it actually really empty if we don't know, if everything's probabilistic, Mm-hmm. And so actually, sometimes it's not. And what ends up happening is there are these particle and antiparticle pairs that just pop into existence, and then they annihilate each other and go away.
Just cause?
Because probability.
Like it?
Just because probability.
Oh my God.
It's not 100% probability that there's nothing there. And so they'll just pop up and they'll annihilate and go away. And so,
That's allowed?
Yeah, actually it is allowed.
Wait, that's wrong. Isn't there some conservation of whatever, you can't make something out of nothing?
Yeah, but, there's a particle and antiparticle, so they balance it out.
Oh, that's freaking wild. Okay.
Yeah, it's pretty crazy to think about that there could be something in nothing. It's pretty crazy. So, basically, Einstein's equation equals mc squared, mm-hmm. right? So that means that matter is basically energy, and energy is matter, and there's this relationship between energy and mass. Mm-hmm. And so, basically, if the vacuum has these particles that have mass, that means that the vacuum has some energy. So that's what we call the vacuum energy. Mm-hmm. And so, basically, with these two concepts, now we can start talking about how black holes die. So, you can imagine at the very, very edge of a black hole, there could be this pair of particles, like a particle and antiparticle pair, pop up. And what if it was just outside, one was just outside the barrier of the black hole, and one was just inside the barrier of the black hole? So only one fell into the black hole.
Oh yeah, you call that event horizon?
Yeah, it's the event horizon. Good job.
One gets sucked in and one doesn't.
Yeah, one can escape if it's just right at the barrier.
But it can also not escape, right? Maybe?
Yeah, maybe. So, if we imagine this very edge case scenario where one does and one doesn't, then what we would see is the particle that escaped. Because we can't see anything that goes into the black hole, because it just eats it up. And so what we see is this black hole like emitting all these particles, but that doesn't really follow the laws of conservation of energy, right? It's just producing these particles from nowhere. That's what we see. And so in order to explain that, we explain that by saying that the antiparticles, or the particles that fall into the black hole, are basically like getting rid of some of the mass or some of the energy within the black hole to conserve energy.
What if the positive one goes in instead of the anti one?
Well, it's the same thing.
Oh,
we explain it the same way. Like, it needs to have the opposite of the mass in order to like, cancel out or whatever. And so, some of the black hole needs to disappear in order to conserve energy.
I see.
Or mass, or they're the same thing, right?
Yeah.
Wow. So basically, if you do this so many times, right, the black hole will get smaller and smaller and smaller, and then it'll eventually disappear, and go away, and it'll die.
Wow. Wow, that's cool. Hey, you know how they tell us like Earth is gonna eventually be swallowed up by a black hole? You just throw some particles at it and be like, go away.
Yeah. Yeah. So like, because we can only see these particles that are being emitted by the black hole, a lot of people think of this death scenario as like a steaming cup of coffee. So like this cup of coffee is like emitting, like basically, you know, emitting all this steam, right? And if you leave it out long enough in the sun, it'll disappear, right?
Yeah.
All the particles will go into the air. So that's what people like to compare it as.
Oh, that's nice.
Yeah.
Does anything get left behind?
No, it just like
It's gone?
goes into the universe, and all the particles are just spread out throughout the universe.
And then everything is balanced again, kind of thing?
So this is what we call like, it's a certain type of death of the universe. So there are lots of different ways the universe could die, and this specific scenario where all of the energy and all of the mass in the universe is spread out like evenly, that's one of the ways.
Oh my god.
It's kind of sad, right?
That's scary.
There's no more matter anywhere. It's just like all spread out and in these random particles everywhere.
Oh, that's so weird. Dude, F.
Yeah, big F.
Yeah. Oh.
Yep.
Dude, space is kind of scary.
Yeah, it is pretty scary.
Wow.
Well, thank you for joining me, Stephanie.
Yeah, thanks for having me.
And that was the first level of talking about black hole deaths. Now we'll move on to the next level. Okay.
Hi, this is my friend Jamie, who is taking the same class as I am, and we're also going to be talking about how black holes die. So, we're both taking this black hole class, so we both already know what black holes are, but my specific question is, how do black holes die? So, there are several different views of black hole death, but like all are kind of categorized underneath this umbrella term of Hawking radiation. Have you heard of it, Jamie?
Yeah, I have heard a lot about it. Like, so actually, I'm very interested in about how black hole dies because, like, when I was young, I thought the black hole would just stay there forever. It doesn't die. But right now, like, I learn more about black holes, and now I know that black hole can evaporate using Hawking radiation. So I'm so excited about like, I know that like from some kind of thermodynamics, black hole can evaporate and it has like the temperature called Hawking radiation, but I also want to know more about it. So maybe I will ask Kylie about like what Hawking temperature is. So do you have any opinion or any things like you want to say about Hawking temperature?
Yeah, sure. So let me talk a little bit about what exactly it means for a black hole to evaporate first. And then we can talk about what this temperature is. So basically, there are many different physical explanations for this Hawking radiation evaporation phenomenon. I'll go through some of them. So the most probably easiest one to comprehend is there are particles and antiparticles in the universe, and the vacuum of space isn't really a vacuum. You've taken quantum mechanics, so you probably understand like there are these pairs of particles and antiparticles that will pop up and annihilate each other and disappear and stuff. And so what we can imagine is one of these pairs popping up at the event horizon, and you can imagine it right on the barrier, so that one of them gets pulled in, but the other doesn't. And so if one particle goes in, to us viewing the black hole from the outside, it looks as if just some random particle is emitted because we don't see what happens past the event horizon. And so in order for conservation of energy and conservation of mass to kind of stay in effect, there needs to be something to counteract the particle we see being emitted. And so we say that the black hole's energy or the black hole's mass has decreased when we see this particle being emitted. And there are several like physical explanations for that. So one is that we claim the particle that falls into the black hole has negative mass or negative energy. And so because it has negative stuff, then it cancels out some of the mass already in the black hole. Yeah, that's one of the physical explanations. Another one is that like we imagine that there are two photons that just randomly pop up. So the antiparticle and particle pair is a pair of photons. And one is pulled into the black hole and another isn't. And in the case of the photon doesn't have mass. And so how are we supposed to explain this kind of thing? And so the way we explain it is that there's also kind of a partner wave that also falls into the black hole with the other photon, and that partner wave has a negative energy. And so that cancels the mass in the black hole. So like, those are two of several like physical explanations for that. So that kind of leads into your question about the temperature. So these particles that we see being emitted by the black hole, they can kind of be characterized by a black body curve. And so we just take the temperature of that black body curve as the temperature of the radiation from the black hole.
Wow, I see. So yeah, it's very amazing. It's very amazing that like, I never thought about it before. About like, I know that some black hole can emit like the particle out of it, and the mass of the black hole can be decreased. But yeah, I never thought about the negative mass or negative energy that comes into the black hole. And now, yeah, it's very interesting mechanism because I never heard about any like particle with negative mass or something that can decrease the mass of the black hole. So that's a new insight for me.
Yeah.
And yeah, so do you know why the temperature of the black hole is the same as like the black body temperature? Like why does the spectrum or like the black body curve, like the temperature of the black hole is in the same curve as the black body radiation?
So the radiation we see from the black hole, as long as it's not like consuming any mass, right, is just this Hawking radiation. And so because it's just that, then because the Hawking radiation has this black body curve nature, then we just assign that as the temperature of the black hole.
Oh wow, yeah, that's very interesting. And do you know how fast the black hole evaporates?
Yeah, so it's actually quite an amazingly long time. So if we think of just like a stellar mass black hole that is pretty common, right? Stars explode, go supernova, and they make these pretty common stellar mass black holes. Like a black hole with one solar mass takes like 10 to the 67 years to evaporate, which is much longer than the age of the universe. So we shouldn't expect to see any of these black holes just evaporate that are stellar mass. But like interestingly enough, I did see that primordial black holes, which is Jamie's topic, yay!
Yeah, that's my topic.
Primordial black holes could potentially be visible in this dying phase because they potentially could have lower mass. So that was exciting and kind of an interesting link between my topic and Jamie's topic.
Yeah, that's true. Like I searched some information about that too, and it's very interesting. Like I know that when black hole dies, like during the last phase, we can call it as like the explosion of black hole because the radiation rate is so high that it just like explode. So it will be a very observed. Yeah.
Wow, that's so exciting.
Yeah.
Well, thank you for joining me today, Jamie. And
thanks a lot.
Yes. Let's move on to the next level of discussion.
Now let's talk about the deaths of black holes in a more technical perspective. So how do we measure the temperature of a black hole? Well, we can do that by thinking about the Unruh Effect, which states that an accelerated observer, in comparison to an inertial observer, will see some kind of background radiation in their reference frame. So why is that important? Well, at the event horizon of a black hole, which is where we want to be viewing this radiation, because that's where the radiation is being emitted, an observer at the event horizon needs to be constantly accelerating in order to be stationary there. And so that's why the Unruh Effect kind of comes into play. And so if we, set the Unruh Effect in equilibrium with the radiation from the black hole, we can find the temperature. And how can we do that? Well, the Unruh Effect and the black hole, the radiation they emit is kind of like a black body. It's a black body. And so each black body has an associated temperature with it. And so if we use that, as well as setting them in equilibrium with each other, we find that the temperature turns out to be Planck's constant times the speed of light cubed, all over 8 pi g kb times the mass of the black hole. And if we plug in all of those constants, we find that the temperature becomes 6 times 10 to the negative 8 Kelvin, all over the mass of the black hole in terms of like solar masses. So what can we glean from this? We can glean that the black hole actually gets hotter as it loses this mass, because it goes as 1 over the mass of the black hole. So what does this mean? It means that as long as the black hole isn't consuming any more energy or mass, then it'll just get faster. It'll start to evaporate faster and faster and faster and faster. It'll start to go away faster, 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 faster over time as it gets smaller. And so what is this time length that it would evaporate away at? So we can use the thermodynamic relation of du dt, change of u, over time, which equals 4 pi r squared sigma t to the 4th, and put in for r the event horizon distance, event horizon radius, and for t, what we just found, what we just talked about for t, the temperature. And for a non-rotating uncharged black hole, we get that this time scale, this lifetime of the black hole, is about 5,120 pi g squared m cubed all over Planck's constant times c to the 4th. And if we plug in all those constants, we get 2.1 times 10 to the 67 years times the mass of the black hole cubed. And make sure it's in solar masses, of course. So this is a super, super, super long time. And if we plug in, for example, like a stellar mass black hole, which are pretty common, you'd say, like these huge stars, they explode, they die, and they leave behind these solar mass black holes. So if we put in one of those common black holes, its lifetime is longer than the known age of the universe. What kind of implications does that have? It means that if we were to look out into the universe for these dying black holes, we wouldn't find any that are solar mass, because they haven't died yet. They're all still there. So how are we supposed to find or test our theories about these dying black holes? Well, what scientists are thinking, is that we could potentially see dying primordial black holes, because these primordial black holes might have masses that are smaller than solar masses, and so we might be able to see them dying out in the universe. So that's one of the current things that people might be looking into. Another problem regarding this process of black hole death is the Transplankian problem. So if we trace, for example, for this problem, if we trace the frequency of an emitted photon back to the event horizon where it was emitted, the frequency actually goes to infinity. So what does that mean about the wavelength? It means that the wavelength is infinitely short, or a Transplankian wavelength, so to speak. And this causes all sorts of problems, because, it's not supposed to be that short. And so, a lot of theorists are like, oh, what do we do about this? And so this is one of many examples of problems in a field of physics called quantum gravity. And quantum gravity is basically the intersection, or what theorists are trying to intersect, of gravity and quantum mechanics. Basically, gravity works on very large large distance scales, and quantum mechanics works on very short distance scales. So putting them together is very difficult, and these are the kinds of problems that quantum gravity theorists are trying to work on. And because black holes deal often with these large distances as well as these small distances, they actually are very good laboratories for these problems that quantum gravity theorists are working on. And so by studying them, we will in turn learn more about the inherent physics of the universe. And that's pretty cool. Hey, thanks for watching this video. Don't forget to like, subscribe, and leave your favorite fun fact about black holes down in the comments. See you around!